Welcome, everyone. Today, we're diving into the mathematics of curves. And we're going to unlock this surprisingly simple, super elegant formula that helps us measure, well, pretty much everything from the crust on your pizza to the path of a planet. So let's kick things off with a riddle you've definitely seen, but maybe never really thought about. Why in the world are sprinters' starting blocks staggered on a curved track? I mean, it looks totally unfair, right? But it's actually the complete opposite. And by the end of this explainer, you'll know the precise mathematical reason why.
Okay, so to solve our riddle, we first need to reach into our math toolkit and grab a really crucial tool. And that tool is something you probably remember from trigonometry class, the radian.
So what even is a radian? It's not just another way to measure an angle, like degrees. It's way more fundamental than that. It's a pure natural relationship between the length of an arc and the circle's radius. And this definition right here, theta equals s over r, this little ratio is the key that's going to unlock everything for us. Because if we take that definition we just looked at and just do a tiny little bit of algebraic shuffling, we uncover one of the simplest, most powerful formulas in all of geometry. And here it is, s equals r times theta. This is the hero of our story today. All you need is the radius of a circle and its central angle, in radians of course, and you can find the exact length of any piece of its curve. It's clean, it's powerful, and it's incredibly useful. And what's so great about this little formula is just how versatile it is. It's like a Swiss Army knife. If you need the arc length, you use it as is. But hey, what if you know the arc length and need to find the radius or the angle? You just rearrange it. It's a whole toolkit in one simple equation. All right, enough theory. The best way to really get a feel for a formula is to see it in action, right? So let's put this thing to the test with a few examples. Let's start with a really basic one. We've got a radius of 10 centimeters and an angle of pi over 4 radians. We literally just plug those values straight into our formula. S equals 10 times pi over 4. That gives us an arc length of 5 pi over 2 centimeters, which is about 7.85 centimeters. Simple as that. Okay, now for a problem that's a little more delicious. We have a 14-inch pizza, and we want to know how long the crust is on a 45-degree slice. Now, pay close attention to step 2 here. This is absolutely critical. We can't just plug 45 degrees into the formula. We have to convert it to radians first. So 45 degrees becomes pi over 4. Then we can multiply by the radius, and we find out our crust is about 11 inches long. So what if we've got it the other way around? What if we know the length of the curve and we need to find out how big the circle is? No problem. Here, the arc length is 24 pi meters and the angle is 2 pi over 3 radians. We just use our rearranged formula. R equals S divided by theta. We plug in the numbers, do the math, and boom, the radius is exactly 36 meters. You know, I really hammered that conversion step in the pizza problem for a reason. It is the single most common mistake people make with this formula, and this next slide shows you exactly why you have to avoid it. It's a big deal. Just look at the difference here. It's night and day. On the left, if you forget the rule and just multiply the 10-centimeter radius by 45 degrees, you get a completely ridiculous answer of 450 centimeters. That's not even close. But on the right, when you do the right thing and convert 45 degrees to radians first, you get the correct answer, about 7.85 centimeters. The formula S equals R theta only works with radians, because the formula itself comes directly from the definition of a radian. That's the key. Okay, so we've got the formula, we know the one critical rule we can't break, and we've seen how it works. I think it's time. Let's go back to our opening puzzle and finally solve that racetrack riddle. And here is the solution. It's actually pretty simple. Each lane on that track is part of a circle, but they all have a different radius. If you're running in an outer lane, your radius, r, is larger. And since arc length s equals r times theta, a larger radius means you have a longer curve to run. So that staggered start, it's just compensating for that extra distance. It's what makes sure everyone runs the exact same length to the finish line. It's all about fairness. And this whole idea isn't just for sports, it is all around you. Engineers use this exact formula to design the sweep of your car's windshield wipers to make sure they clear enough glass for you to see. It's absolutely fundamental for designing a curved bridge or, say, analyzing a satellite's orbit. So there you have it. We've gone from the simple definition of a radian all the way to understanding the design of everyday objects, which leaves us with a final question. Now that you have this tool to precisely measure any curve, what other shapes, paths, and patterns in the world around you can you start to understand? Think about it.